Hello and good evening. You know what? To maintain the relevance of my first few words, please watch this in the evening. Thank you. Anyway, today we are going to learn a thing or two, hopefully, about wave optics. A mild warning to those who are easily offended and or disturbed by bad diagrams and handwriting. Because trust me, my handwriting can become worse than a doctor's prescription. And my drawings are often compared with modern art. I don't know whether that's a compliment or not. But don't worry, I've tried my best to make my content readable and understandable. Let us start with a story. There's a lake in my city which surprisingly has very still water. I often stand beside its edge, looking at my own reflection, thinking out loud, I wish I was less ugly. My cousin would then come along and throw a pebble into the lake. It would distort my reflection. Then he would say, There, you look better now. I would then proceed to give him a beating. But we are not here to talk about that. We are more interested at the events happening at the lake. When the pebble hits the lake, you'll see that there are ripples or waves formed, something like this. In fact, in reality, most stationary sources produce waves like these. You have sound waves are similar to like this. Even Wi-Fi, if you closely look at the symbol for Wi-Fi, it's something like this. So it's actually a part of the complete description of the waveform. The complete waveform actually looks something like this, whereas the symbol represents only a part. Wait, let me just complete that. Yeah. But what about light? You actually might have performed this experiment at school, and if you haven't, you can do it at home as well. All you require is a light source, three cardboard cutouts with three holes in each one of them, such that they are in a straight line. Now, suppose you are the observer standing over here. If all these three holes are in a straight line, you should be able to observe this light source easily. However, if any one of the three holes or the source itself is moved, you won't be able to observe it. So you can say that light travels in a straight line. And I know that you must be going, wow, that is painfully obvious, but this experiment is not precise. Light, as a matter of fact, has dual nature, both particle nature as well as wave nature. How you say? Now, that is a completely different topic altogether, which we are not going to get into this time. But remember, light can be treated as a wave, and this makes things quite interesting. We'll see how. Suppose there are two people inside a room. This room is separated by a wall with a small gap. Now, this is person number one, this is person number two. Suppose the length of this wall is 100 meters. Even if person number one shouts at the top of his voice, there's a fat chance that person number two won't be able to hear him at all. However, if this distance was reduced to a single meter, even if person one says something like, well, great Scott, person number two would be able to hear him. Sound waves would move and bend around the obstacle, that is the wall, to reach person number two. Heavy, right? So, when the distance was 100 meters, light wasn't able to bend. However, when you reduced this distance to a significantly lower value, waves were able to bend around it, the obstacle. So light too, because of its wave nature, should be able to bend around obstacles, right? But there's a catch. What is it? The obstacles need to be small, very, very small. How small? Less than half a micrometer. That's how small they need to be. So, the experiment which I discussed earlier, realize what's the fault in it? The obstacle was just too damn big. Now that we are done with some trinkets and details about waves and wave nature of light, let's move towards some terminologies which will help us understand Huygens principle. Let us consider the case of the pebble and the lake. When we drop a pebble in the middle, it will create ripples. Suppose at time t is equal to 0, this is the ripple which is formed. The points A and B on this wave have a tendency to move outwards. At time t is equal to t naught, they will have formed a bigger ripple which will have a common center, which means the point A and point B have the same velocity, that they are in phase. This initial ripple is a collection of such points. This set of points which move at the same velocity, that is, cover the same distance for a finite amount of time, is called a wavefront. And judging by the shape, you can say that this is a circular wavefront. Before we move on, I have a small question to ask. What shape is this? Oh no, please keep your eyebrows down. I'm not being retarded here. Yes, this looks like a straight line, but the accurate answer is a bit philosophical, you can say. Let me explain how. Suppose the size of this page was only this much. I would have drawn this straight line like this, and yes, it still looks like a straight line until I think outside the box and break boundaries. Now, it might seem, once I break boundaries, like a triangle or a bigger rectangle. More importantly, like a really large circle. So what does this have to do with waves? Let us see. Suppose we have a light source over here. It is going to dissipate its light in a form something like this. So the radius is going to keep on increasing. And now we have an observer far, far away, somewhere over here. By the time this circular wavefront comes and hits this observer, the radius of the circular wavefront will be so large that it would appear as a plane wavefront for this observer. So in short, we can say that an incoming spherical wave from a very large distance will appear as a plane one. So this shown here, although appears like a plane wavefront, but it's actually a circular wavefront of a very large radius. But this is a pretty good approximation which we can use for further analysis. That covers the fundamentals of wave optics. It would be easier for you to grasp further concepts like Huygens principle and much more. I hope you learned something new today. Constructive criticism is always welcome. Thank you for your attention. Have a good day.